Hello, this is a number theory video on greatest common divisor. GCD is greatest common divisor. A synonym is GCF, greatest common factor. Greatest common divisor and least common multiple are used again and again when working with fractions, when working with equivalent fractions, adding and subtracting, common denominators. In fact, the common denominator, the least common denominator, is the least common multiple. Putting fractions in lower terms, putting fractions in higher terms. Our goal here in a number theory class is to understand the foundations and underpinnings of greatest common divisors and least common multiples. Okay, let's look at our textbook, section 1.5, greatest common divisor. Definition. Definition 2. The greatest common divisor of two integers, a and b, is the greatest integer that divides both a and b. Now, this is a little bit crude, but I think I'm going to go ahead and take a peek here at Wikipedia. If you're in this class, you probably have worked with greatest common divisors before, but in case you haven't lately, the beginning way of doing greatest common divisor is to list the divisors. The example that they do here in Wikipedia is the greatest common divisor of 54 and 24. The listing method. The divisors of 54 are here. The divisors of 24 are here. Oops. Divisors of 24 are here. Then you might circle, for example, the common divisors, the divisors that are in both lists. The common divisors are 1, 2, 3, and 6. Therefore, the greatest common divisor of 54 and 24 is 6. The notation that we use for greatest common divisor is the parentheses. So in example 8, the greatest common divisor of 24 and 18 is 6. Here's our notation. A and B in parentheses means the greatest common divisor of A and B. It does look like an ordered pair, but in the context, we know that it's greatest common divisor. We will assume the following. Any common divisor will divide the greatest common divisor. If you say that over to yourself a couple times, it should make sense. Symbolically, here is our statement. If the greatest common divisor of A and B is D, and we have a number X that divides A and divides B, X must divide D. If we come back to our book, definition 3, two integers A and B are relatively prime if and only if the greatest common divisor is 1. This seems like a trivial definition, but it is far from trivial. Being relatively prime is very important. Let's see some examples of relatively prime numbers. 7 and 10 are relatively prime. The only common divisor for 7 and 10 is 1. The greatest common divisor for 8 and 15 is 1. Notice that the numbers themselves do not need to be prime. It is certainly the case if you take two prime numbers, the greatest common divisor is 1. The concept of being relatively prime is very important in number theory. In middle school, we don't use the term relatively prime, but we have the concept of relatively prime. If you have a fraction with the numerator and denominator not having any common factors, we know that it is in lowest terms. For example, the fraction 7/12 is in lowest terms because there is no common factor other than 1. The next thing we need to talk about is prime factorization. We're going to be talking a little bit more about primes in upcoming sections. So if you need to do a quick little review of prime numbers, do that. But prime factorization, let's say, for example, we want the prime factorization of 12. We're going to make a factor tree. 2 times 6, 2 times 3. My prime numbers here are 2, 2, and 3. So the prime factorization of 12 is 2 to the second power times 3. There's a nice app at the math playground for doing factor trees. So let's take a look at that app. Okay, here we are at the math playground, and this is an excellent site. And here's the factor trees. Unfortunately, this is a Flash program, so you have to install Flash. And this does have two features here, finding the prime factorization of a number and using the prime factorization to find GCF and LCM, which is exactly what we want to do in our college course. So let's just see here. Yeah, 90. So when you're setting this up, you do not have to always use prime numbers. Ultimately, you need to use prime numbers. So 90 is equal to 2 times 3 squared times 5. And you can use this to find the least common multiple and greatest common divisor of two numbers like 84 and 54. And we're going to be doing that here by hand, but you might want to play with it here on the math playground. Okay, I'd like to do this example together. Find the prime factorization of each number and use the prime factorizations to find the GCD. So you might do a factor tree for 120 and 924 slightly ahead of me here. So for 120, we might start with 2 and 60, and maybe 6 and 10, 2 and 3, 2 and 5. Students often like to circle the prime numbers and not circle the numbers that are not prime. So 120 is equal to 2 to the third power times 3 times 5. And it's a good idea to check that either by hand or with a calculator. 924. So now we're going to be using our divisibility tests. 2 does go in here because it's an even number. Might as well do it the easy way if possible. 2 goes in again, 231. Now 3 goes in here because 2 plus 3 plus 1 is 6, and 3 divides into 6. That's our divisibility test for 3. 3 times 77, and 77 is 7 times 11, and so 7 and 11 are prime. So my prime factorization of 924 is 2 squared times 3 times 7 times 11. Now you might think about how we're going to form the greatest common divisor. Here's how we use prime factorization to find the greatest common divisor. First, find the prime factorization of each number. Use each of the common factors, each to the lowest power they appear in the original numbers. Multiply out to get the GCD. I highly recommend you write this down. Now let's go back to our example. Looking at the proof here, we have A over D and B over D. And we're going to show that for these two numbers, the only positive divisor is 1. So we're going to take a number K and let it be a positive common divisor of A over D and B over D. That is, K divides A over D and K divides B over D. As a result, we have two positive integers, m and n. Km equals A over D and Kn equals B over D. This is using the definition of divides from week 2. We use this definition frequently in week 2, and we will use it frequently throughout the course. Multiplying through by D, we get the equations A equals KMD and B equals KND. KD is a common divisor of both A and B. We could write that this way. KD divides A, that's from this statement, and KD also divides B, that's from this statement. KD is greater than or equal to D because it's a multiple of D. However, D is the greatest common divisor of A and D. Therefore, K must be 1. Now, the author has committed a cardinal sin here. They did not end their proof with what they're trying to prove. the final line of the proof needs to be that A over D and B over D have a greatest common divisor of 1. This concludes the proof. Now let's move on to Theorem 8. Let A, B, and C be integers. The greatest common divisor of A and B is equal to the greatest common divisor of A plus CB and B. I call this the contamination theorem. So let's write that down. So this is saying that if you take one of the letters and take some multiple of it, it might be a positive multiple or a negative multiple, and add it into the other number, it does not change the greatest common divisor. That's rather striking. Example 10 is an example of the contamination theorem. Greatest common divisor of 4 and 14. Maybe we didn't know the greatest common divisor of 4 and 14. So I'm leaving the first number as 4. By the way, you can contaminate either the first number or the second number. Greatest common divisor is symmetric. The greatest common divisor of A and B equals the greatest common divisor of B and A. So I'm leaving the first number the same as 4, and I'm taking the second number, 14, and I'm adding to 14 negative 3 times 4. Well, negative 3 times 4 is 12. 14 minus 12 is 2, so I have the greatest common divisor of 4 and 2, and obviously the greatest common divisor of 4 and 2 is 2. So this contamination theorem is one method of finding greatest common divisor. It may not be an efficient method, but it is one method. Now we have Theorem 9. Theorem 9 is a 3-star theorem. It is very important. It's one of the most important theorems in the course. Sometimes it's labeled Bezout's theorem. The greatest common divisor of two integers, A and B, not both 0, is the least positive integer such that MA plus NB equals D for some integers M and N. For emphasis, let's write down here that the greatest common divisor of A and B is D. MA plus ND is a linear combination of A and B. We introduced the idea of linear combination last week, and now we're seeing a very important application of this. So let's do an example. Let's play with 6 and 10. And let's make some linear combinations. (6x) plus 10y, where x and y are elements of the integers. So x and y could be 1. 6 times 1 plus 10 times 1 equals 16. 16 is a linear combination. X could be -1. And y could be +1. That's -6 and 10, which is 4. X could be 3. And y could be -2. I'm making up numbers here. 18 and -20 is -2. -2 is a linear combination of 6 and 10. 6 times 2 is 12 plus 10 times negative 1 is equal to positive 2. And positive 2 is the smallest positive number that I can get doing a linear combination. I cannot combine 6 and 10 to make 1. The greatest common divisor of 6 and 10 is 2. This is an example of our theorem. Linear combinations are huge in this course. Now I'd like to go on to our next example. Find the greatest common divisor of 15 and 20, and then find a linear combination of 15 and 20 that gives your answer to part A. I hope you can see that the greatest common divisor of 15 and 20 is 5. This is not designed to be tricky. This first week on GCD, we're mainly understanding the notation. And the linear combination is going to be 15 times negative 1 plus 20 times 1 to give 5. Once again, we're mainly learning the terminology and the notation. By the way, the definitions here on page 23, I think, are good to read. This is where you're finding the greatest common divisor of a long list of numbers rather than just 2. Most of the time in our course, we're going to be doing the greatest common divisor of 2 numbers, but it can be extended to more than 2 numbers. Now I'd like to do number 6 from the book. Prove the following. If m and n are integers that are relatively prime, m and n having a greatest common divisor of 1, show that the greatest common divisor of m plus n and m minus n is 1 or 2. You might experiment with some numbers. They're relatively prime. And I'm going to have you pause the video to see if you can generate some examples that give a GCD of 1 and a GCD of 2. I would like to go straight now to the proof. We're going to let the GCD of m plus n and m minus n equal d. We will show d equals 1 or 2. That's our goal. Well, d is a common divisor. That's what this means. So d must divide m plus n, and d must divide m minus n. And now we're going to be using our theorem 9, Bezout's theorem. D must divide the common divisor. I'm sorry, I misspoke. We are not going to be applying Bezout's theorem. We're going to be applying theorem 4, which says that if we have a common divisor, the common divisor must divide a linear combination. So D has to divide m plus n plus m minus n, a very simple linear combination. That is, D divides 2m. D also has to divide another linear combination. The next linear combination I want is 1 times m plus n and negative 1 times m minus n. And if you distribute the negative 1 through there, we get the opposite of m plus n. So therefore, D divides 2n. So D is a common divisor of 2m and 2n. The greatest common divisor of 2m and 2n, I'm going to pull out the common factor of 2. 2 times the greatest common divisor of m and n. And we might need to prove that result over on the side sometime. But for right now, we'll assume that that's true. But we had the greatest common divisor of m and n was 1. That was a given piece of information. Let's check that. Yes, it was given that the greatest common divisor of m and n was 1. 2 times 1 equals 2. D here is a common divisor of 2m and 2n. So therefore, D has to divide the greatest common divisor. The greatest common divisor of 2m and 2n is 2. So D must divide 2. But the only divisors are 1 and 2. Therefore, D equals 1 or 2. So my final conclusion then is that the greatest common divisor of m plus n and m minus n is equal to 1 or 2. I believe that if you have two odd numbers, the greatest common divisor will be 2. And in many other cases, the greatest common divisor is 1. So you should be able to find examples for each. Okay, the last example I'd like to do in this video is to do number 7. Show that if m is a positive integer, the numbers 3m plus 2 and 5m plus 3 are relatively prime. So let's look at some quick examples. If m is 1, 3 times 1 plus 2 would be 5, and 5m plus 3 is 8. 5 and 8 is going to have a common divisor of 1. If m equals 2, we get 6 plus 2, which is 8, and 13. The greatest common divisor of 8 and 13 is 1. Those are relatively prime. Let's take some big number like 5. 5 times 3 is 15, and 2 is 17, and 28. Those are relatively prime. Kind of striking that no matter what m is, we get two numbers here that are relatively prime. Well, our big hammer here is Bezout's theorem, that if I can find a linear combination of these two numbers to give 1, that is the greatest common divisor. So I want to have a linear combination of 3m plus 2 and 5m plus 3 to get 1. This is my goal, which means I want my m's to cancel out because I want 1, and I do mean 1. I think what works here is going to be -5 in the x position and +3 in the y position. No, I take that back. Let's use +5 in the x position and -3 in the y position. Let's see if this works. distributive property here, I get 5 times 3m is 15m plus 10. And distributive property over here, I get negative 15m minus 9. This was what I wanted to be true. And in fact, I get 1. So I have found a linear combination of 3m plus 2 and 5m plus 3 to be 1. So therefore, the greatest common divisor of these two numbers is 1. This brings this video for greatest common divisor to a close. Have a great day.